The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
This is very exciting. In the previous lecture, we learned all about buffer overflow attacks. And today we're going to continue to discuss some techniques to launch these attacks. So the basic idea of all these buffer overflow attacks is as follows. So first of all, they leverage a couple different facts. So one thing that they leverage is that system software is often written in C. And so by system software, I mean things like databases, compilers, network servers, things like that, right? And you can also think of things like your favorite command shell. All those types of things are typically written in C. So why are these things typically written in C? Well, they're written in C because our community, of course, is obsessed with speed, right? And so C is supposed to be like high-level assembly. It takes us very close to the hardware. And so as a result, all of these very sort of mission-critical systems are written in this very low-level language. Now, the problem with things being written in C is that C actually exposes raw memory addresses. Right? And so not only does it expose raw memory addresses, but it also performs no bounds checking when programs manipulate those raw addresses. Right? And so as you can imagine, this is a recipe for disaster. Okay? So once again, why doesn't C check these bounds? Well, one reason is because the hardware doesn't do that. And people who write in C typically want the maximum amount of speed possible. Right? The other reason is that in C, as we'll discuss later, it can actually be very difficult to determine the semantics of what it means to have a pointer that's actually in bounds. So in some cases, it would be very difficult for the C runtime to automatically do that. Now we'll discuss some techniques which will actually try to do that type of automatic inference. But as we'll see, none of these techniques are fully bulletproof. And so these attacks also leverage knowledge of the x86 architecture. And by knowledge of that architecture, I mean things like what's the direction that the stack grows, right? What are the calling conventions for functions, right? When you invoke a C function, what is the stack going to look like? When you allocate an object on the heap, what are those heap allocation structures going to look like? And so let's look at a simple example. It's very similar to something that you saw in the last lecture. So we've got your standard read request up here. And then you've got a buffer that's here. And by now, you've probably trained your lizard brain instincts. Whenever you see a buffer, you're probably filled with fear. That is the right attitude. So we've got the buffer up here. And then we've got the canonical and I. And then we've got the infamous gets command. Right, and then you've got some other stuff here. Right, so as we discussed in lecture last week, this is problematic, right? Because this gets operation here does not actually check the bounds on the buffer. So what can happen is that if the user actually supplies the buffer, actually I should put that guy up here, for example. If that buffer comes in from the user, and we use this unsafe function here, then we can actually overflow this buffer, and we can actually rewrite stuff that's on the stack. So just as a reminder of what that stuff looks like, let's look at a stack diagram here. So let's say here we've got I. Let's say here we've got buff. right? So we've got the first address buffer here. We've got the last one up here. I apologize for my handwriting. I'm used to writing on the marker board. You should pray for me. So anyways, so then up here, we've got the saved value of the break pointer. We've got the return address for the function there. And then we've got some other stuff from the previous frame. Right? And so don't forget, we've got the stack pointer, which goes there. And then we've got the new break pointer, which goes here. The entry stack pointer goes there. And then somewhere up here, we've got the entry break pointer. Right? So just as a reminder, the way that the Stack Overflow works is that basically it goes this way, right? So when the gets operation is called, we start writing bytes into buff, and eventually it's going to start overwriting these things that are on the stack. And so this is basically, should all look pretty familiar to you. So what does the attacker do to take advantage of that? It basically supplies that long input. And so the key idea here is that this can be attacker supplied, right? And so if this return address is attacker supplied, then basically the attacker can determine where this function is going to jump to after it concludes its execution. So what can the attacker do once it's actually been able to hijack that return address and jump wherever it wants? Well, basically, the attacker is now running code with the privileges of the process that it's just hijacked, for example. So if that process was a high priority process, let's say it was running as root or admin or whatever they call the super user in your favorite operating system, then now that program, which is controlled by the attacker, can do whatever it wants using the authority of that high priority program. So it can do things like it can maybe read files, it can send spam, let's say if you corrupted a mail server. It can even do things like actually defeat firewalls. Right? Because the idea of a firewall is that there's going to be this distinction between good machines that are behind the firewall and bad machines that are outside of the firewall. So typically machines that are inside of the firewall, they have a lot of trust with each other. Right? But if you can subvert a machine that's actually inside of the firewall, right, that's great, because now you get to sort of skip past a lot of those checks that those machines don't have because they think that you're a trusted individual. So one thing you might be thinking, right, I remember I was thinking this when I was a student, was, OK, fine, so I've showed you how to do this buffer overflow, but why didn't the OS stop this? Right? Isn't the OS supposed to be that thing that's sort of sitting around like Guardians of the Galaxy and preventing all this kind of evil stuff from happening? Well, the thing to note is that the OS actually isn't watching you all the time. Right? The hardware is watching you all the time, right? Because it's the thing that's actually fetching instructions and decoding them and doing things like that. But to a first approximation, what does the OS do? It basically sets up some page table stuff, and then it basically lets you, the application, run. And if you ask the operating system for services, so for example, you want to send a network packet, or you want to do some IPC or things like that, then you'll invoke a system call, and you'll actually trap into the OS. But other than that, the operating system is not sort of looking at each and every instruction that your application is executing, right? So in other words, when this buffer overflow attacks, it's not like the operating system was looking at each one of these memory accesses for signs of chicanery, right? All this address space belongs to you, the subverted process, right? So you get to do with it what you want to do with it, right? Or at least this is the whole C attitude towards life, right? Live fast, die young. So that's why the operating system can't help you right there. So later in the lecture, we will discuss some things that the operating system can do with respect to the hardware so that it can help protect against these types of attacks, right? But once again, it's actually just the hardware that's interposing on every little thing that you do. So we can actually take advantage of some of that stuff, for example, using special types of page protections and things like that we'll discuss a little bit later. So that's basically an overview of what the buffer overflow looks like. So how are we going to fix these things? So one fix for avoiding buffer overflows is to simply avoid bugs in your C code. right? So this has the nice advantage of being correct by construction, right? If you don't have any bugs in your program, ipso facto, the attacker cannot take advantage of any bugs. That's I'm a professor. I get paid the big bucks to think deeply like that. Now, this, of course, is easier said than done, right? There's a couple of very straightforward things that programmers can do to practice good security hygiene. So for example, like functions like this gets function, right? These are kind of like go-tos. These are now known to be bad ideas, right? So when you compile your code and you include functions like this, if you're using a modern compiler, GCC, Visual Studio, whatever, it will actually complain about that. It'll say, hey, you're using one of these unsafe functions. Consider using, fgets or using a version of sprintf that actually sort of tracks the bounds of things. So that's sort of one simple thing that programmers can do. But note that a lot of applications actually manipulate buffers without necessarily calling one of these functions, right? This is very common in network servers and things like that. They'll define their own custom parsing routines to make sure that things are extracted from the buffers in the way that they want. So just restricting yourself to these types of things won't solve the problem completely. So another thing that makes this approach difficult is that it's not always obvious sort of what is a bug in a C program. So if you've ever worked on a very large-scale system that's been written in C, you'll know that it can be tricky if you've got some function definition that takes in 18 void star pointers. I mean, only Zeus knows what all those things mean, right? And so it's much more difficult in a language like C that has sort of weak typing and things like that to actually understand as a programmer what it means to have a bug and what it means to not have a bug. Okay, so in general, one of the main themes that you'll see in this class is that C is probably the spawn of the devil, right? And we use it because, once again, we typically want to be fast, right? But as hardware gets faster and as we get more and better languages to write large-scale systems code, we'll see that maybe it doesn't always make sense to write your stuff in C, even if you think it has to be fast, right? So we'll discuss some of that later in later lectures. So that's one approach, avoiding bugs in the first place. So another approach is to build tools that allow programmers to find bugs. And so an example of this is something that's called static analysis. Now we'll talk a little bit more about static analysis in later lectures, but suffice it to say that static analysis is a way of analyzing the source code of your program before it even runs and looking for potential problems. So imagine that you have a function like this. So the popularly named foo function, it takes in a pointer. Let's say it declares some integer offset value. It declares another pointer and adds the offset to that pointer. Now, even just at this moment in the code, right, static analysis can tell you that this offset variable is uninitialized, right? So essentially, you can do things like saying, is there any control flow through this program by which offset could have been initialized before it was actually used in this calculation here? Now, in this example, it's very simple to see that the answer is no, right? You can imagine that if there were more branches or things like this, it'd be more difficult to tell. But one thing that a static analysis tool could tell you, and in fact, one thing that popular compilers will tell you, is you'll compile this and it'll say, hey, buddy, this has not been initialized. Are you sure this is what you want to do? Right? So that's one very simple example of static analysis. Another example of what you can do is, let's say after this we had a branch condition here. Right? So we say if the offset is greater than 8, then we'll call some function bar and pass in the offset. Now, one thing you can note about this is that this branch condition here actually tells us something about what the value of offset is, right? Ignoring the fact that it wasn't initialized, we do know that once we get here, we know that offset actually has to be greater than 8. So in some cases, what we can do is actually propagate that constraint, that notion that offset must be greater than 8, into our analysis of bar, right? So when we start statically analyzing bar, we know that offset can only take certain values. Okay, so once again, this is a very high-level introduction to static analysis. We'll discuss it more in later lectures. But this is a basic intuition of how we might be able to detect some types of bugs without even executing your code. So does that all make sense? And so another thing you think about doing, too, is what they call program fuzzing. So the idea behind program fuzzing is that essentially you take all of the functions in your code and you essentially throw random values for input to those functions, right? And so the idea is that you want to have high code coverage for all of your tests, right? So if you go out in the real world, typically when you check in unit tests, you can't just do things like, I tried values 2, 4, 8, and 15 because 15 is an odd number, so I probably tested all the branches, right? What you actually have to do is you have to look at things like I said, how many branches in the program overall were actually touched by your test code, right? Because that's typically where the bugs hide. The programmers don't think about the corner cases, and so as a result, they do have some unit tests that pass. They may even have bigger tests that pass, but they're not actually hitting all the corner cases in the program. So static analysis can actually help with this fuzzing here, once again using things like this notion of constraints. So for example, in this program here, we have this branch condition here that's specified with offset being greater than 8. So we can know what that offset is statically, so we can make sure that if we're automatically generating fuzzed inputs, we can ensure that one of those inputs hopefully will ensure that somehow offset is less than 8, one will ensure that offset's equal to 8, one will ensure that it's greater than 8. So does that all make sense? Cool. So that's the basic idea behind the notion of building tools to help programmers find bugs. So the nice thing is that even sort of partial analysis can be very, very useful, particularly when you're dealing with C. A lot of these tools that we'll discuss to prevent against things like buffer overflow or initialized variables, they can't catch all the problems, right? But they can actually give us sort of forward progress towards making these programs more secure. Now, of course, the disadvantage of these things is that they're not complete, right? And so forward progress is not complete progress. And so it's still a very active area of research of how you defend against security exploits in C and just in programs in general. So those were two approaches to deal with defending against buffer overflows. There's actually some other approaches. So a third approach you might think about using is to use a memory-safe language. And so examples of these are things like, Python, Java, C#. We're not going to put up Perl there because people use Perl are bad people. So you could use a memory-safe language like that. And this, to a certain extent, seems sort of like the most obvious thing that you could do, right? So I just told you over there that basically C is high-level assembly code, and it exposes raw pointers and does all these things that you don't want it to do, and it doesn't do things you do want it to do, like check bounds. So why not just use one of these high-level languages? Well, there's a couple of reasons for that. So first of all, there's actually a lot of legacy code that's out there. Right? So it's all fine and dandy if you want to go out and start your new project and you want to write it in one of these memory-safe languages. But what if you've been given this big binary or this big source code distribution that's been written in C, it's been maintained for 10, 15 years, it's been this generational project, I mean, our children's children will be working on it, right? You can't just say, I'm just going to write everything in C# and change the world, right? And this isn't just a problem with C, for example. There's actually systems that you use that you should be afraid of because they actually use Fortran and COBOL code. What? It's like stuff from the Civil War, okay? So why does that happen? Well, once again, the reason why it happens is because as engineers, we kind of want to think like, oh, we can just build everything ourselves. It'll be awesome. It'll be just the way that I want it. I'll call my variables the things that I want. But in the real world, that doesn't happen, right? You show up on your job, and you have this thing that exists, and you look through the code base, and you say, whoa, why doesn't it do this? And they say, listen, okay, we'll deal with that in V2. But for now, we got to make things work because the customers are taking away their money. Right? So there's basically this huge issue of legacy code here, and how do we deal with it? And as we'll see with the baggy bounds system, one of the nice advantages of it is that it actually interoperates quite well with this legacy code. Right? So anyways, so this is one reason why you can't just necessarily make all these buffer overflow problems go away by using one of these memory-safe languages. So another challenge is that, what if you need low-level access to hardware? Right? This might happen if you're writing something like a device driver or something like that. So in that case, you really do need sort of the benefits that C gives you in terms of being able to look at registers and actually understand low-level interrupts and things like that. There's another thing too, which people always bring up and which I've alluded to before, but it's performance, right? So if you care about performance, typically the thing that you're told is you've got to write it in C. Otherwise, you're just going to be so slow, you're going to get laughed at Code Academy or whatever. Now, this is increasingly less of an issue, right, the perf stuff, because people have actually gotten very good with doing things like making better compilers that have all kinds of powerful optimizations. And also, there are these things called JITs, which actually really reduce the cost of using these memory-safe languages. So have you guys heard of JITs before? So I'll give you a very brief introduction to what it is. The idea is that think about a language like, let's say, Java or JavaScript. It's very high level. It's dynamically typed, right? It has automatic heap management, things like that. So typically, when these languages first came out, they were all just interpreted, right? And by interpreted, I mean they didn't actually execute raw x86 instructions. Instead, these languages were compiled down to some type of intermediate form. You may have heard of things like the JVM, the Java Virtual Machine bytecode, things like that, right? And basically, you had a program that sort of sat in a loop and took these bytecodes and basically executed the high-level semantic instruction that was encoded in that bytecode. So for example, some of the JVM bytecodes dealt with things like pushing and popping things up on the stack, right? So you just have a program that would sort of go through a loop and sort of operate that stack and simulate those operations. Okay, so that all seemed fine and dandy, but once again, all the speed freaks out there were like, what about the perf? This is too slow, right? You've got sort of that interpreter sitting in that loop and sort of getting in the way of our bare metal performance. So what people started to do is actually take these high-level interpreted languages and dynamically generate x86 code for them on the fly, right? So in terms of just-in-time compilation, that means I take your snippet of JavaScript, I take your snippet of Java or whatever, and I actually spend a little bit of time up front to create actual raw machine instructions, raw x86 that will run directly on the bare metal. So I take that initial performance hit for the JIT compilation, but then after that, my program actually does run on the raw hardware, right? And so things like the perf argument are not necessarily as compelling as they used to be because of stuff like JIT. There's also some crazy stuff out there like asm.js. So we can talk more about this offline if you actually are a JavaScript hacker. But there are actually some neat tricks that you can do by compiling down JavaScript to a very restricted subset of the language that only operates on arrays, right? And so what this allows you to do is actually get rid of a lot of the dynamic typing overhead you have in standard JavaScript. And you can actually get JavaScript code now to run within 2x of raw C or C++ performance, right? 2x might sound like a lot, but it used to be it's things like 10x or 20x. So we're actually making a lot of progress on that front. And so the other thing to keep in mind with performance too is that a lot of times you don't need performance as much as you might think that you do, right? So think about it like this. Let's say that your program is actually I/O bound. Okay, so it's not CPU bound. In other words, let's say that your program spends most of its time waiting for network input, waiting for disk input, waiting for user input, things like that. In those types of cases, you don't actually need to have blazingly fast raw compute speed, right? Because your program actually isn't spending a lot of time doing that kind of stuff, right? So once again, this perf argument here, you got to take this stuff with a grain of salt. And I actually see a lot of students who struggle with this. So for example, I'll ask someone to go out and write me a very simple program to parse a text file. So they spend all this time trying to get this to work in C or C++, and it's super fast and uses the templates and all that kind of stuff. But it's like a one-line solution in Python, right? And it essentially runs just as fast, and you could develop it much, much easier. So you just got to take these perf arguments with a grain of salt. So anyway, so we've discussed 3 ways that you can possibly avoid these buffer overflows. So just avoid bugs in the first place. Lol, that's difficult to do. Approach 2, you can build tools to help you discover those bugs. And then approach 3 is, in a certain sense, you can push those tools into the runtime, and you can actually hopefully rely on some of the language runtime features to prevent you from seeing raw memory addresses, and to do things like bounce checking and so on and so forth. But once again, as we discussed before, there's a lot of legacy C and C++ code out there. So it's difficult to sort of apply some of these techniques, particularly number 2 and number 3, if you've got to deal with that legacy code. So how can we do buffer overflow mitigation despite all these challenges? Besides just dropping out of computer science classes and becoming a painter or something like that. So what actually is going on in a buffer overflow? So in a buffer overflow, the attacker exploits two things. So the first thing that the attack is going to exploit is gaining control over the instruction pointer. Right? And by this, I mean that somehow the attacker figures out some place in the code that it can make the program jump to, against the program's will. Now, this is necessary but insufficient for an attack typically to happen. Because the other thing that the attacker needs to do is basically make that pointer point to malicious code. Right? So how are we going to basically make that hijacked IP instruction pointer point to something that does something useful for the attacker? So what's interesting is that in many cases it's often fairly straightforward for the attacker to put some interesting code into memory. So we looked at some of those shellcode attacks from last lecture, where you can actually embed that attack code in a string. As we'll discuss a little bit today and more in the next lecture, you can actually take advantage of some of the pre-existing code that the application has and jump to it in an unexpected way to make some evil things happen. Right? So typically, figuring out what code the attacker wants to run, maybe that's not as challenging as actually being able to force the program to jump to that location in memory. So, and the reason why that's tricky is because basically the attacker has to know in some way where it should jump to, right? So as we'll see in a second, and as you actually saw in last lecture, a lot of these shellcode attacks, they actually take advantage of these hard-coded locations in memory, right, where the instruction pointer needs to get set to. So some of the defenses that we're about to look at can actually randomize things in terms of like code layout, heap layout, and make it more difficult for the attacker to figure out where things are located. So let's look at one simpler mitigation approach first. So this is the idea of stack canaries. Right? And so the basic idea behind stack canaries is that during a buffer overflow, it's actually OK if we allow the attacker to overwrite the return address if we can actually catch that overwrite before we actually jump to the place that the attacker wants us to go. Okay? So basically, here's how it works. So let's return to yield stack diagram. Essentially, we have to think of it as like a magic value, basically in front of the return address, right? Such that any overflow would have to sort of hit the canary first and then hit the return address. And if we can check that canary before we return from the function, then we can detect the evil. So let's say that, once again, we've got the buffer here. Then we're going to put the canary here. And then this will be the saved value of the break pointer. And then this will be the return address. So once again, remember the overflow goes this way. So the idea is that if the overflow wants to get to that return address, it first has to trample on this canary thing here, right? So you have a question?
Why does it have to touch canary?
Well, because assuming that the attacker doesn't know how to sort of jump around in memory sort of arbitrarily, right? The way that traditionally these buffer overflow attacks work is that you sort of look in GDB, you sort of figure out where all this stuff is, and then you just essentially just have this string, this array that sort of grows this way, right? Now you're correct that if the attacker could just sort of go here directly, yeah, then all the bets are off, right? But in the very simple buffer overflow approach, everything basically just has to grow sort of strictly that way, right? And so the basic idea behind the canary is that we allow the buffer overflow exploit to take place. But then we have runtime code that at the time of the return from the function is going to check this canary and make sure that it has the right value, right? And so it's called a canary because, back in the days when PETA wasn't around, you could use birds to test for evil things, and so that's why it's called canary.
And my question is, if the attacker is able to overwrite the return address, right, and modifying the canary, how is the check that the canary was not modified is going to be performed? Because so the attacker overwrites the return address, right? So how is the check that the canary was modified?
Yeah. So basically, you have to have some piece of code that will actually check this before the return actually takes place, right? So in other words, yeah, you're right. There has to be that ordering there, right? So essentially, what you have to do is you have to have support from the compiler here, right? That will actually extend the calling convention, if you will, such that part of the return sequence is before we actually treat this value as valid, make sure this guy hasn't been trampled. Then and only then can we then jump somewhere else.
I feel like I might be jumping the gun here, but doesn't this assume that the attacker can't just find out or guess what the canary value is?
That, in fact, is the very next thing in my lecture notes. If I had prizes, you'd get one. I don't have any, but good for you, gold star. That's exactly correct, right? So, one of the next things I was about to say is, what's a problem with this scheme, right? What if, for example, on every program, we always put the value A, just like a bunch of, four values of A, because this is like a single 32-bit word, right? Then you'd have that exact problem that you just mentioned, right? Because then the attacker, this kind of gets back to your question, he or she knows how big this is, right? This is deterministic on every system. So you just make sure that your buffer overflow has a bunch of A's here, right? And then you overwrite this stuff. So you're exactly right about that. And so there's basically different types of values you could put here in this canary to try to prevent that, right? So one thing that you can do here is you can use this. This is sort of a very funny type of canary, but it basically exploits the ways that a lot of C programs and C functions handle special characters. So imagine that you use this value for the canary. Okay, so the binary value 0, which is like the null byte, right, the null character in ASCII, right? Carriage return, line feed, and then the -1, right? So what's funny about this is that a lot of the sort of functions that you can exploit, right, that manipulate strings, for example, they will stop when they encounter one of these words or one of these values, right? So like imagine that you're sort of using, some string manipulation function to go up this way. It's going to hit that null character. Oops, it's going to stop processing, right? Or maybe if you're using sort of a line-oriented function, right? Carriage return line feed, that's often used as a line terminator. So once again, you're using that dangerous function. It's trying to go this way. It hits that. Oops, it's going to quit, right? And the -1 is sort of another similar magic token. So that's one way you can get around that. Yeah, 1 second. And then another thing you can do is you can use a randomized value, right? So here, you just sort of punt on this whole idea of trying to figure out what exactly it is that might cause that attack to terminate, and you just pull some random number out of the ether, making it difficult for the attacker to guess what that is, right? Now, of course, this random value, its strength is basically based on how difficult it is for the attacker to guess that, right? So if the attacker, for example, can understand that maybe there's only, let's say, 3 bits of entropy in your system, then maybe the attacker can do some type of like brute force attack, so on and so forth. So one thing to keep in mind in general is that whenever someone tells you, here's a randomized defense against, attack foo, if there are not a lot of random bits there, that attack may not give you as much defense as you think. I think you had a question?
In regards to the deterministic value, usually what tends to happen is you read from another buffer and you write into that buffer on the stack. So in that situation, it seems like that deterministic canary is kind of useless. Because I read from this buffer, I know what the canary is, and I have this other buffer that I control it, and I never check. In that buffer, I can put as much data as I want. I know the deterministic canary, so I can override it very safely. So I don't see how this really works in what scenarios. Because you're assuming you're reading from the buffer on the stack and you're going to stop at.
Well, we're assuming, so we're writing to the buffer, right? So basically, the idea is that you write some sort of two long strings sort of this way. And then the idea is that if you can't guess what this is, then you can't basically put this value inside of your overflow string.
But like, if you said it's deterministic, right? 0, CR, 1.
Oh yeah. Right. Okay, so I think I understand your question now. Yes. So if you use this system here with the deterministic canary, and you essentially are not using one of these functions from, let's say, like the standard library that would be fooled by this, then yeah, you can defeat the system that way.
But I can use like string CPI, and the destination can be buffer, and the source can be, user input, right? And that would not protect me against that.
So I'm not sure I understand the attack. So
string CPI would take from the user input all my data, would overwrite the canary. And you're saying, I think I understand what you're saying.
right, because the idea is that, yeah, you can fill this buffer with bytes from wherever, right? But the idea is that unless you can guess this, then it doesn't matter, right? But you're correct that, in general, anything that allows you to guess this or randomly get that value correct will lead to a defeat of the system.
In terms of getting enough randomness, can you just take something like the number of seconds or milliseconds since the epoch and use that at the calling time of the function?
Well, so as it turns out, a lot of times calls to sort of get data or things like that don't contain as much randomness as you might think, because the program itself might somehow, let's say, for example, have a log statement or a function you could call to sort of get the time that the program was launched or things like that. But you're right, in practice, if you can use something, let's say like the hardware system clock, which is often sort of like the lowest level, better system of sort of time randomness, yes, that kind of thing might work.
But even if you can pull the log phone, it still depends on exactly what time you issue the request. And so if you don't have control over how long it takes for your request to get from your computer to the server, then I don't think you can deterministically guess exactly the right time.
That's right. I mean, the devil's in the details with all this kind of stuff, right? So in other words, if there's some way for you to figure out, for example, that type of timing channel, right, you might find out that the amount of entropy, the amount of randomness, is not, let's say, the full size of a timestamp, but maybe something much smaller, right? Because maybe the attacker can figure out the hour and the minute in which you did this, but not the second, for example. But yeah, so we'll take one more question and then we'll move on.
I was just going to say, for the record, like trying to roll your own randomness is usually like a bad idea, right? Like usually
that's correct.
They're supplied by the system.
Oh yes, yeah, that's very true. It's kind of like inventing your own crypto system, which is another popular thing undergrads sometimes want to do. We're not the NSA, we're not mathematicians, that typically fails. So you're exactly right about that. But even if you use system-supplied randomness, you still may end up with fewer bits of entropy than you expect. And I'll give you an example of that when we talk about address-space randomization. So that's basically how the stack canary approach works. And so since we're in a security class, you might be wondering, so what kinds of things will stack canaries not catch? So when do canaries fail? Right, so one way that they can fail is if the attacker overwrites things like function pointers. Right? Because if function pointers get hit, there's nothing that the canary can do to prevent that type of exploit from taking place. So for example, let's say you had code that declared a pointer. It gets initialized in some way, it doesn't really matter. Then you have a buffer here. Once again, the gets function rears its ugly head. And then let's say down here, we assign some value 5, let's say, to the pointer. Right? Now note that we haven't actually tried to attack the return address of the function that contains this code. Right? When we do the buffer overflow, this pointer address up here is going to get corrupted. Right? And so what ends up happening is that if the attacker can corrupt that pointer, then the attacker is able to write 5 to some attacker-controlled address. right? So does everyone see how the canary doesn't help here? Because we're basically not attacking the way that the function returns.
Won't the pointer be below the buffer?
Won't the pointer? So yeah, so you're worried about, is it going to be here or is it going to be here?
Or I'm worried about will you actually be able to access where the pointer is when you're overflowing?
Yeah. So you can't necessarily, so it's a good question. So I think in a lot of the previous examples, you've been assuming that this guy would be sort of here, like in the stack. So if the stack is growing this way, then the pointer would be down here. But the order of the particular variables, it depends on a bunch of different things. It depends on sort of the way that the compiler lays stuff out. It depends on sort of the calling convention of the hardware, so on and so forth. But you're right that if the basically, if the buffer overflow was going this way, but the pointer was sort of in front of the buffer, yeah, then this wouldn't work.
Why can't you associate the canary with the function just like you did with the return address?
So that's an interesting point. So you could do those things, right? In fact, you could try to imagine a compiler that whenever it had any pointer whatsoever, it would always try to add padding for various things, right? So as it turns out, schemes like that will quickly get expensive in terms of like all the code that's sort of added to have to check for all those types of things, right? Because then you can imagine that every single time you want to invoke any pointer or call any function, you've got to have this code that's going to check whether that canary is correct. But yeah, in principle, you could do something like that. So does this make sense? So we see that canaries don't help you in this situation. And so another thing, as we discussed before, is that if you can guess the randomness, then basically the random canaries don't work. And producing sort of secure sources of randomness is actually a topic in and of itself. That's very, very complicated. So we're not going to go into great depth about that here. But suffice it to say, if you can guess the randomness, everything falls apart.
So canaries usually have less bits in the return address. Otherwise, can't you just memorize the return address and check if that has changed?
Let's say, so you're saying if the canary here is, let's say, smaller than...
So I'm saying, like, the part of the canary is that you know what that value is, and then at runtime you check if it's been overridden. Like, can't you also, like, memorize the return address value and check if that's been changed?
Can't you? Oh, so you're saying can't the secure system, can't it look at the return address and figure out if that's been changed? And then otherwise, yeah. So in other words, if there, well, let me say that. Yes and no. So note that there's still this that's going to get overwritten in a buffer overflow attack. So this may still cause problems. But in principle, if somehow like that, these things were invariant somehow, then yeah, you could do something like that. But the problem is that in many cases, this return address, the bookkeeping overhead for that would be a little bit tricky, right? Because you can imagine that a particular function may get called from different places, and so on and so forth. And so just in the interest of time, so we're going to zoom forward a little bit. But then if we have time at the end, we'll come back to some of these questions. So, all right, so those are some situations in which the canary can fail. There's some other places in which it can fail too. So for example, one way that it might fail is with malloc and free attacks. So this is sort of a uniquely C-style attack. So let's see what happens here. So imagine that you have two pointers here, P and Q. And then imagine that we issue mallocs for both of these. Right? We give P 1024 bytes of memory. We also give Q 1024 bytes of memory. And then let's say that we do a stir copy on P from some buff that's controlled by the attacker. Okay, so here's where the overflow happens. And then let's say that we free Q. And then let's say that we free P. Okay, so it's fairly straightforward code, right? 2 pointers, we malloc some memory for each one of them. We use one of these unsafe functions, the buffer overflow happens, then we free a Q and we free P. So let's assume that P and Q, the memory that's assigned to them, are nearby in terms of the layout, in terms of memory, right? So both of these objects sort of lie next to each other in the memory space. So there's some subtle and sort of evil things that can happen here, right? Because this stir copy here might actually it'll sort of fill P with a bunch of stuff, but it might also corrupt some of the state that belongs to Q. Okay, and this can cause problems. And some of you may have done things like this unintentionally, right? In your own code, when you have some type of weird use of pointers, and then stuff sort of seems to work, but then when you call free later on, it's seg faults or something like that, right? What we're going to talk about here is a way that an attacker can sort of take advantage of that behavior. And we're actually going to explain why that happens. So imagine that inside the implementation of free and malloc, an allocated block looks like this. So let's say that there is, the app visible data that lives up here. And then let's say you had a size variable down here. This is not something that the application sees directly, right? But this is sort of like some bookkeeping info that the free or the malloc system sort of tracks, so it can know the sizes of the buffers that it allocated. So let's say that a free block has some metadata that looks like this. Right, so maybe you've got the size of the free block here, and then you've got a bunch of empty space here. And then let's say, this is where things get interesting, you've got a backwards pointer, and then you've got a forward pointer. And maybe you got some size data here. Now, why are we having these 2 pointers here? Well, it's because the memory allocation system, in this case, is using sort of like a doubly linked list to sort of track, how the free blocks are related to each other, right? So when you allocate a free block, you take it off of this doubly linked list, and then when you deallocate it, you do some pointer arithmetic, and then you fix these things up, and then you add it back to that linked list, right? So as always, whenever you hear pointer arithmetic, you should think chicanery, right? Because that's where a lot of these problems come about. And so the thing to note is that we had this buffer overflow here, right, in P. If we assume that P and Q are next to each other or very close in memory, then what can end up happening is that this buffer overflow can overwrite some of the size data for the allocated pointer Q, right? So is everybody with me so far? Because if you're with me so far, then basically you can sort of use your imagination at this point and sort of see where things go wrong, right? Because essentially what's going to end up happening is that these free operations, they look at this metadata to do all kinds of pointer manipulations with this kind of stuff, right? So you can basically think of it as, get rid of this guy. Somewhere in the implementation of free, it's going to get some pointer based on the value of size, right? Where size is something the attacker controls because the attacker did the buffer overflow, right? So then you can imagine that it does a bunch of pointer arithmetic, right? So it's going to look at the back and the forward pointers of this block, and then it's going to do something like update the back pointer and also update the forward pointer. right? And the exact specifics of this you don't need to worry about, right? This is just an example of the code that takes place in there. But the point is that note that because the attacker has overwritten size, the attacker now controls this pointer that's passed into the free code. Okay? And because of that, these two statements here, these are actually pointer updates, right? This is a pointer somewhere, and because the attacker has been able to control this P, he actually controls all this stuff too. So this is where the attack can actually take place, right? So when the free code operates and it tries to do things like, for example, merge these two blocks, right? That's typically why you have things like this double linked list, because if you have two blocks that are adjacent to each other and they're both free, you want to merge them into one big block. Well, we control size. That means we control this whole process here. That means if we've been clever in how these overflows are working, at these points we can write to a memory in a way that we choose. So does that make sense? And like I said, this type of thing often happens in your own code when you're not being very clever with pointers and you make some mistake with double freeing or whatever. This is why stuff will segfault sometimes, right? Because you've sort of messed up this metadata that lives with each one of these allocated blocks. And then at some point, this calculation will point to some garbage value and then you're dead, right? But if you're the attacker, you can actually choose that value and use it for your own advantage. Okay, so now let's get to another approach for sort of getting rid of some of these buffer overflow attacks. And that approach is bounds checking. Right? And the goal of bounds checking is to make sure that when you use a particular pointer, it only refers to something that is a memory object, and that pointer is in the valid bounds of that memory object. Right? So that's the base idea behind the idea. It's actually pretty simple. Right? At a high level. Once again, in C, though, it's very difficult to actually understand things like what does it actually mean for a pointer to be in bounds or out of bounds or valid or invalid. So for example, let's say that you have two pieces of code like this. So you declare a character array of 1024 bytes. And let's say that you do something like this. You declare a pointer, and then you get the address of one of the elements in X. Right? So does this make sense? Right? Is this a good idea to do that? It's hard to say, right? I mean, if you're treating this X up here as a string, right? Maybe it makes sense, for example, to take a pointer like this, then you can increment it and decrement it because maybe you're looking for some special value of a character in there. But if this is maybe like a network message or something like that, maybe there's actually some struct that's embedded in here. So it doesn't actually make sense to sort of walk this character by character, right? So the challenge here is that, once again, because C allows you to do whatever you want, it's hard to determine what it is you actually wanted to do, right? And so as a result, it's a little bit sort of subtle with how you define things like pointer safety in C. And so you can also imagine that life gets even more complicated if you use structs and unions. So imagine you had a union that looked like this. It's got some integer value in there. And then you've got some struct. And then it has two integers inside of it. Oops. Right, so don't forget the way that the unions work is that basically the union is going to allocate the maximum size for sort of the largest element. But at any given moment, you typically expect that either this int I will be valid or this struct s will be valid in the union, but not both. Right? So imagine that you had code that did something like this. You get a pointer to the address of this guy. Right? So I get an integer pointer to the address of, in the union, this struct, and then k. Well, I mean, that address, this reference is strictly speaking in bounds, right? There's memory that's been allocated for this. That's not incorrect. But I mean, are you actually at this moment in the program execution treating this union as one of these guys or one of these guys? It's hard to say, right? So as a result of these sort of ambiguous pointer semantics that can arise in these C programs, typically these bound checking approaches, they sort of can only offer a weaker notion of pointer correctness. And so that notion is as follows. So if you have a pointer p prime that's derived from a base pointer p, then p prime should only be used to dereference memory that belongs to that original base pointer. Right? So for a derived pointer in p prime that's derived from some original 1p, then p prime should only be used to dereference memory that belongs to p. So note that this is a weaker goal than enforcing completely correct pointer semantics, right? Because, for example, you could still have weird issues like with this union here, for example. Maybe at this particular point in the program, it wasn't correct for the program to be able to reference that particular value in the union, right? But, you know, at least this pointer reference is sort of in bounds, right? So maybe, you know, in this example up here, maybe this sort of creation of this pointer here sort of violated the sort of semantics of the network message embedded in X. But at least you're not trampling on arbitrary memory, right? You're only trampling on memory that belongs to you. And so in the world of C, this is considered success, right? So you have to be happy for the small things. So that's the basic idea. Now, the challenge with sort of enforcing these types of semantics here is that in many cases you need help from the compiler. Okay, so you need help from the compiler, and you typically need to recompile programs to enforce these semantics. So that can be a drag for backwards compatibility. But this is the basic notion of sort of bounds checking. So what are some ways that you can implement bounds checking? So one very simple way is this notion called electric fences. Right? And so the notion here is that for every object that you allocate on the heap, you allocate a guard page that's sort of immediately next to it, right? And you set the page protections on that page such that if anybody tries to touch that, you get a hard fault, right? The hard rule will say that's out of bounds, and then the program will just stop right there, right? And so this is a very simple thing that you can do, right? And what's nice about this approach, actually, is that whenever you have an invalid memory reference, this causes a fault immediately, right? If you've ever debugged a big C or C++ program, one of the big problems is that a lot of times when you corrupt memory, that memory sort of is corrupted silently and sort of for a while, and it isn't until later that something crashes, and then only then you realize something happened, but you don't know what that something is. These typically lead to what they call Heisenbugs, right? Things that have this notion of uncertainty in them. So what's nice about this is that, you know, as soon as the pointer sort of hits here, boom, hits the guard page, everything blows up. All right. Now, can you think of a disadvantage with this approach?
Takes a lot of extra space.
Yeah, exactly. So, you know, imagine that this heap thing here was super, super small, but then I've allocated a whole page just to make sure that my little tiny thing here didn't have like one of these pointer attacks, right? So this is very space intensive. And so like people don't really deploy something like this in production, right? This can be useful for debugging things, but you would never do this for a real program. Does that make simple? So these electric fences are actually pretty simple to understand.
Why does that have to be so large necessarily?
So the reason is because this guard page here, you're typically relying on the hardwares like page level protection to deal with those types of things. And so there's like certain minimum sizes you can set for the size of a page, like according to the hardware. So typically like that page is 4K, for example. So getting back to your question, if this is some like super small value here, then yeah, this is like, maybe 2 bytes or whatever, but then you got like 4K here protecting it.
Are you protecting just the heap or individual things that you want?
Oh, sorry, yeah. So by heap, I mean like heap object. Yeah, thank you for clarifying. Yeah, exactly. So, imagine like for each malloc you do, you could have one of these, a separate guard page for it.
And you do it below and above or just above?
You can do either.
You tend to worry about overflows above, but there could also be underflows.
That's right. That's right. Yeah, you could do either. But once again, depending on this, on the size of the object, now you've got to declare 2 guard pages, right? So now this, sort of quickly gets out of control. But yeah, you could have a bookending once, basically. So that's the basic idea behind that. Actually, yeah, we can erase this guy. And then another approach you could look at is what they call fat pointers. And so the idea here is that you actually want to modify the pointer representation itself to include bounds information in it. So, if you look at your regular 32-bit pointer, what's it look like? Well, it's just 32 bits, and then you got an address in it, right? If you look at a fat pointer, then one way you could think about looking at this is you've got a 4-byte base, and then you have a 4-byte end. So in other words, this is where the allocated object starts. That's where it ends. And then you've got a 4-byte cur address. So this is where the pointer actually is within that bounds, right? So basically what happens is that the compiler will sort of generate code such that when you access these fat pointers, this gets updated, but it'll also check these 2 things to make sure that nothing bad has happened during that update. So for example, you can imagine that if I had code like this, so I have an int pointer, and then I allocate 8 bytes. So assuming that we're on a 32-bit architecture, this should point to 2 integers, space for 2 integers. And then I have some while loop that is going to just assign some value to the pointer and then increment the pointer. What you'll see is that the current address for this pointer, like at this point in the code, will point to the base, right? And then every time we sort of iterate through here, we can see that we are either checking a bound or incrementing a bound, right? So at this point, when we want to dereference it, we can actually check and see is the current address of that pointer in this range. And if it's not, we can throw an exception here, so on and so forth, right? So, and once again, where is this taking place? This is taking place in new code that the compiler generated. So one question that came up on the online discussion group, some people were saying, what is instrumented code? What does that mean, right? So when I say that the compiler generates new code, imagine that this is what you see as a programmer, but sort of before this operation actually takes place, imagine the compiler inserted some new C code here that basically looked at these base bounds here, and then if there was something out of bounds, it would then do an exit or an abort or something like that. Right? So that's what it means to say that there is instrumented code. It's that you take the source code, you as the programmer C, add some new C source code, and then compile that bigger program. Right? So the basic idea, I think, behind the fat pointers is pretty simple. There's some disadvantages to this. The biggest disadvantage is that, oh my goodness, look how big your pointers are now. Right? And so what this means is that you can't just take a fat pointer and pass it to an unmodified off-the-shelf library. right? Because it may have certain expectations that pointers are a certain size, and when you give it this thing, it's gonna blow up. You also have trouble if you want to include these types of pointers in structs or things like that, because that can actually change the size of the struct, right? And so a very popular thing in C code to do is to take like size of a struct, you know, and then like do something as a result of that, like reserve some disk space for a struct of that size, so on and so forth. So this causes all that stuff to blow up, right? Because once again, the pointers have gotten very, very big. And another thing which is a bit subtle, but it's that these fat pointers typically will not be able to be updated in an atomic fashion, right? So on 32-bit architectures, typically if you do like a write to a 32-bit variable, that write is atomic, right? But now these pointers are these 3 integer-sized things, right? So if you have any code that takes advantage of the fact that it expects pointer writes to be atomic, then you may get in trouble here, right? Because you can imagine that to do some of these checks, you have to sort of look at the current address and then look at this, and then you might have to increment that, and so on and so forth. So this can cause very subtle concurrency bugs if you have code that depends on that atomicity of the writes. So does that all make sense? So that's one approach you could do. But kind of like electric fences, this has some sort of nasty side effects that means that people don't typically use that in practice. So now we can start talking about bounds checking with respect to the shadow data structures that are mentioned in the baggy bounds paper. So the basic idea for these shadow data structures is for each object that you allocate, you want to store how big the object is. Right? And so for example, if you have some pointer that you call malloc on, right, you need to store that size of that object there. And then note that if you have something that's like a static variable, like this, right, the compiler can sort of automatically figure out what the bounds are for that thing there, right, statically speaking. So for each one of these pointers, we need to interpose somehow on 2 operations. So basically, we need to do arithmetic. So this is things like q equals, p plus 7, or whatever. And then you want to, interpose on dereferencing. So this is something like, q equals, a, or something like that. So what's interesting is that you might think, well, why can't we just rely on dereference when we interpose on stuff, right? Why do we have to look at this sort of point arithmetic here? And similarly, you might wonder the other thing. Like in other words, why can't we just deal with one of these and not have to interpose on both? So we can't just signal an error if we see the arithmetic going out of bounds, because in C, that may or may not be an error, right? So in other words, a very common idiom in C and C++ is you might have a pointer that points to one past the valid end of an object, right? And then you use that as a stop condition, right? So you iterate through the object, then once you hit that end pointer, that's when you actually stop the loop or whatever, right? So if we just interpose on arithmetic, and we always cause a hard fault when we see a pointer go out of bounds, that may actually break a lot of legitimate applications, right? So we can't just interpose on that. And so you might say, well, then why can't we just interpose on dereferencing and just sort of, when we notice that you've sort of touched something out of bounds, we'll just raise the error there. Well, the challenge there is that how do you know it's out of bounds, right? It's the arithmetic interpositioning that essentially allows us to tell, whether or not this thing is going to be legal here, right? Because it's the interpositioning on the arithmetic that allows us to sort of track where the pointer is with respect to its original base bounds. Right, so that's the basic idea there. And so the next question is, how do we actually implement the bounds checking system? Because basically, we need some way to map a particular pointer address to some types of bounds information for that pointer, right? And so a lot of your previous solutions use things like, for example, like a hash table or a tree, right, that would allow you to sort of do lookups, right, in the standard way. So given a pointer address, I do some lookup in this data structure, figure out what the bounds are. Given those bounds, I can then sort of figure out if I want to allow the access to take place or not. Now, the problem with that is that it's a slow lookup, right? Because these data structures, think if it's a tree, right? You're going through a bunch of branches before you can actually hit the value potentially. And even if it's a hash table, what if there's an overflow in the buckets? You've got to, follow chains or do linear probing or things like that. So the baggy bounds paper that we are about to look at actually figures out a very efficient data structure to track some of these bounds, to make that bounds checking very fast. So let's just step into that right now. But before we go into that, let me very briefly talk about how buddy allocation works, because that's one of the things that came up in a lot of the questions. And so one thing that you'll see for these papers is that a lot of times they are not self-contained, right? So they will mention things that they will assume that you know, but you may not know them. Don't get discouraged by that. That happens to me too sometimes. These papers are sort of written in a way that they assume a lot of prior knowledge, so don't get discouraged by that. Luckily, we actually have access to the internet, so we can look up some of this stuff. I mean, imagine what happened in our parents' time. They just didn't understand stuff. They just had to go home, right? So don't be afraid to look stuff up. We got the Wikipedia. It's mostly correct. So how does the buddy allocation system work? So basically what it does is at first, it treats unallocated memory as one big block, okay? And then when you request smaller blocks for dynamic allocation, it tries to split that address space using powers of 2 until it finds a block that is just big enough to work. So let's say that a request came in. Let's say A is going to equal to malloc 28. 28 bytes. And let's just say in this toy example, there's only 128 bytes of memory total. So the buddy allocator is going to look at this and say, well, I have 128 bytes of memory, but it's too wasteful to allocate this whole thing to this 28-byte request. So I'm going to split this request in 2 and then see if I have a smaller block that's just big enough. So it's going to say, OK, I split this as 0 to 64 and 64 to 128. OK, but this block here is still too big, right? Basically what the buddy allocator wants to do is find a block such that the allocated data in the real object, 28 bytes, is at least half the size of that block. Right? So buddy allocator says, OK, this thing over here is still too big. So what it's going to do is it's going to split the memory space again. Right? So from 0 to 32. And then it's going to say, OK, 28 bytes, that is more than half the size of this block here. So now this block is going to be allocated to A. OK? And so it gets this address here. Now, let's say that we have another request that comes in for B, and let's say that we want a malloc 50. Right? So what's going to happen is that the buddy allocator will say, OK, I actually have a block here that's big enough. Right? 50 is greater than half the size of this thing, so I'll just allocate that right there. So we have the system, or the setup where we have A is here. And then we have B here. And then let's say we had another request that came in for 20 bytes. This is actually pretty straightforward because we can put that right here, right? So then we have something that looks like this. And then what's interesting is that when you deallocate memory, if you have 2 deallocated blocks that are next to each other in the same size, the buddy allocator will merge them into a block that's twice as big, right? So if we had free, let's say C, then we go to this situation. We can't do any merging because this is the only possible block that this one could have been merged with because it's the same size, but this thing's still occupied. So then if we do a free on A, then we have this situation here, right, where these two 32 byte blocks were merged into one of size 64, and then this one of size 64 is still out there, right? So it's called the buddy system because, once again, whenever you have two adjacent blocks that are of the same size and that could be merged to form an aligned block, then the system will merge that buddy with this other buddy and then create that new block that's twice as big, right? So the thing that's nice about this system is that it's very simple to figure out sort of where buddies are, because you can do sort of very cutesy arithmetic, kind of like the buddy bound system, baggy bound system works. But anyways, I'm not going to go into those details. This is basically how buddy allocation works. Does that make sense? Right? And then one question that came up a lot in the online discussion is, isn't this wasteful? Right? So for example, imagine that up here at the beginning, I had a request for size 65 bytes. Right? So if I had a request for 65 bytes, I would allocate this whole structure up here, and then there's actually, you're out of dynamic memory. Right? You can't do any more allocations. And the answer is yes, that is wasteful, but once again, it's sort of a trade-off, right? Because it's very easy to do these calculations of how to do merging and stuff like that. So if you want sort of finer grain allocation, there are other algorithms for that. It's outside the scope of the lecture, so we can talk about that offline if you want. That's basically how the buddy, the buddy allocator works. So what is the baggy bound system going to do? Well, it is going to rely on a couple of tricks. So the first idea is you round up each allocation to a power of 2, and you align the requests to that power of 2. Right, and so essentially the buddy allocator is very nice because it handles a lot of that for you. Right, it sort of naturally will do that kind of thing because that's just the way that it sort of allocates and deallocates memory. And so the second thing that's going to happen, the baggy bound system, is you express each bound as log base 2 of the allocation size. Right? And so what this means, and so why can we do this? Well, once again, all of our allocation sizes are powers of 2. Right? So we don't need very many bits to represent how big a particular allocation size is. So for example, if your allocation size is 16, then you just need, for the logarithm of that, 4 bits to represent the allocation size. Right? So does that make sense? Right? So this is another popular question here. So this is why you only need a small number of bits here, because we're basically forcing the allocation sizes to sort of hit this quantized sort of way, and they can grow. Like you can only have something of, let's say, 16 bytes or 32 bytes. You can't have, for example, 33 bytes. And then the third thing that baggy bounds is going to do is store the limit info in a linear array with 1 byte per entry. But we're going to allocate memory at the granularity of a slot, which in the paper they use 16 bytes as the slot width. So for example, now this next thing, this is 1 bit that wasn't actually explicitly said in the paper, which if you don't sort of grasp would make the paper very tricky to understand. Right? So imagine that you have a slot size which is equal to 16. So if you do P equals malloc 16, so what's going to happen? So in this bounds table, we're going to say take that pointer divided by slot size is going to equal 4, right? So in that bounds table, we're going to put the logarithm of the allocation size in the table. Does that make sense? Okay, now what the tricky thing is, let's say that you had something like this. Right, so let's say that you allocate 32 bytes, right? What is the bounds table going to look like there? So here we actually have to update the bounds table. I'm just going to abbreviate it here T for size reasons. We have to update the bounds table twice. Right, once for the first slot of memory that this allocation takes up, and then a second time for that second slot that it takes up. Right, so once again, 32 is the allocation size. This is the log of that allocation size. So for the 2 slots that this memory takes up, we're going to update the bounds table twice. Does that make sense? Right, and this is really the key that I think for a lot of people sort of makes the paper make sense or not make sense. Right, because you have to update that bounds table multiple times depending on the size of the allocation. Excuse me? Oh yeah, sure. So basically the idea is that you've got this bounds table here, and it's got a bunch of different entries, but it basically needs entries to cover all of P's size, all the allocation size. Okay, so in this case it was very simple because basically this was just one slot in terms of the size. Here it's multiple slot sizes, right? And so what's going to happen is that imagine that we then had a pointer that's sort of moving in the range of P. We have to have sort of a backing table slot for each one of those places where P could be, right? And so once again, it's this second piece here that makes the paper a little bit confusing, I think, because it doesn't really go into depth about that. But this is how that works. Okay, so let's see. So armed with the bounds table stuff, what happens if we have C code that looks like this? So you have a pointer, P prime, you derive it from P, and then you add some variable I. So how do you get the size of the allocation belonging to P? Well, you look in the table using this lookup here. Right? So the size of the data that's been allocated to P is going to be equal to 1, and then you left shift that by looking in the table, taking that pointer value, and then right shifting that by the log of the table size. Right? And this arithmetic works out because of the way that we're sort of binding pointers to the table bounds. Right? So this will get us, this thing right here will get us sort of the log of the size, and then this thing over here basically expands that into like the regular value. Right? So for example, if the size of this pointer were 32 in terms of the bytes that was allocated, right? This is going to get us 5 when we look at it on the table. Then when we left shift it this way, left shift the 1 this way, then we're going to get 32 back again for here. Okay? And then if we want to find the base of that pointer, we take the pointer itself, and then we're going to AND that with the size minus 1. Now what this is going to do is this is actually going to give us sort of a mask, if you can think of it. And that mask is going to allow us to sort of recover the base here. And so imagine that your size equals 16. So 16 equals this in binary, right? So there's a bunch of zeros off this way. Then we've got a 1 here, and we've got some zeros over here. Okay? So if we look at the bitwise inverse of 16 minus 1, then actually, sorry. So if we look at 16 minus 1, so what's that going to look like? 16 minus 1 is going to look like, right, something like this. Okay. So then if we take the inverse of that, what is that going to give us? Right, in binary. So basically, this thing here allows us to basically clear the bits that essentially would be offsets from that valid pointer and just give us the base of that pointer. Okay? And so once we've got this, then it's very simple to check whether this pointer is in bounds, right? Because we can basically just check whether p prime is greater than or equal to base. And whether p prime minus the base is less than size, right? This is just a straightforward thing you do, right? Just seeing whether that derived pointer exists within the bounds we just recovered, right? So at this point, things are pretty straightforward. Now, they have like an optimized check in the paper. I'm not going to go into that in detail, but suffice it to say that all the binary arithmetic, it resolves down to this same thing. They just do some clever tricks there to sort of avoid some of the explicit calculations we do here, right? So that's the basic idea. And so the fifth trick that the baggy bound system uses is that it uses the virtual memory system to prevent out-of-bound dereferences of pointers, right? And so the idea here is that, how much time do we have, by the way? Probably like 0? Yeah. So the basic idea here is that if we have a pointer arithmetic here that we detect as out of bounds, what we can do is actually set the high order bit on a pointer, right? And by doing that, we guarantee that if that pointer is dereferenced, then the paging hardware is going to complain. We're going to throw a hard error, right? Now, in and of itself, just setting that bit does not cause a problem, right? It's only when you dereference that pointer that you get to the problems, okay?